thank Professor Johan Rockstrom for accepting our invitation and agreeing to deliver this lecture. With great pleasure, I welcome Professor Rockstrom to this lecture. Before I request Professor to start his lecture, a few words about him. He doesn't need an introduction to climate change community, but just to complete the formality, I would like to say a few words. Professor Johan Rockstrom is an internationally recognized scientist on global sustainability and Earth's resilience. He led the development of the planetary boundaries framework for human development in the current era of rapid global change. He is deeply involved in research on the future trajectory of the Anthropocene and tipping points in the Earth system. With more than 25 years of experience in applied water research in tropical region, he is also leading scientist on global water resources. Professor Rockstrom is a driving force behind a number of international scientific initiatives, including the Earth Commission and the Planetary Boundary Science Initiative, as well as actively consulting on global sustainability issues for national and multilateral government organizations and business networks. With this brief introduction, I request Professor Rockstrom to deliver his lecture. Thank you.
Thank you so much, Prof. Sati, and great to be with you all for this 21st Grantham lecture. I'll be sharing my screen, and I hope you can see this first page here. What I want to do over the next 45 minutes is to give you a scientific update of humanity's future on planet Earth. In summary, I'll be basically trying to walk you through the state of Earth system science with one key message, which is that we are now having, across multiple strands of scientific analysis and disciplines, evidence that we're putting the stability, the resilience, and the life support on the entire planet at risk, meaning that we need to be very urgently recognizing the need to be stewards of the entire system. In short, that we're no longer a small world on a big, unlimited, resilient planet. We are today a large world on a small, finite, and fragile planet, which is showing its first signs of losing resilience. This means that the science on defining what I call a safe operating space for human development on planet Earth, both in terms of prosperity, but also in terms of equity, is absolutely fundamental if we are to navigate our future in what has now been defined, as I'm sure you're aware, as the Anthropocene. Anthros, Greek for humans, that we've entered a whole new epoch, even though not formalized as a geological epoch yet, but Earth system scientifically very clearly a new epoch where we as humanity are the dominating force of change on planet Earth. And this is, as I'm sure you're also well aware, coming from evidence, not from theory or from models. It comes from empirical observations. It comes from the hockey stick patterns that you see here on this screen. On the left-hand side in red, you have, well, to begin with, the x-axis is the same on all these graphs, actually, from 1750, when we embark on the Industrial Revolution, all the way till today. And they're also the same pattern in terms of the socioeconomic pressures in red on the left-hand side. Up until the mid-1950s, we have incremental increase of socioeconomic pressures from land use to exploiting resources, but it's all linear up until the mid-1950s, and off we go in the great acceleration, the exponential rise of human pressures. And on the right-hand side, you see the impacts on the Earth system, from the classic hockey stick in the upper left-hand corner on carbon dioxide. But you can pick any parameter that matters for human well-being, and it shows the same pattern. Up until the mid-1950s, we have linear increase, incremental increase of pressures. So it's not as if we don't have environmental problems, but they're linear. And then off we go in this exponential phase of rise. And we are today in 2025 reaching a point that I would call a saturation point, where we're starting to see more and more scientific evidence of us hitting the ceiling of hardwired biophysical processes that regulates the very functioning of the Earth system. In short, that we cannot exclude approaching or even being at points of shifts and feedbacks, biophysical feedbacks, that can lead to irreversible changes, what is normally defined as tipping points. When you go from one basin of attraction of a stable system, like a monsoon system over India, or a stable Amazon basin, or a stable Greenland ice sheet, or a functioning AMOC in the North Atlantic, tipping over into a different, first transient, but also fundamentally into another basin of attraction, meaning another logic of functioning. And this is what we are deeply concerned about, because that can self-amplify a journey away from the stable state of the planet that we have been so privileged to have since we left the last ice age some 18,000 years ago. And I'll come back to this. Moving in on climate specifically, because climate in the end is a manifestation of the overall functioning of both the abiotic and the biotic components of the Earth system. We've reached 1.3 degrees Celsius of global mean surface temperature rise when defined in the IPCC, the Intergovernmental Panel on Climate Change terms, of a moving 10-year average. That's the temperature level that is defined in the Paris Climate Agreement as well. So when we talk about breaching 1.5 and having 1.5 as the legally binding target in policy terms, but I would scientifically call it a limit in biophysical terms, it is this 10-year moving average, which we have not reached yet, but we are seeing an indication of a faster rate of warming, particularly as you see here over land area. This is the Berkeley Earth Lab data, but also continuously rising sea surface temperatures in the ocean. And the big concern today, which in a way envelopes this talk that will bring me to the planetary boundary science, is to understand what is happening on planet Earth right now, because we're seeing for the first time a tendency of accelerated warming. And that comes from the temperature records. These are the 5 sources of observations of global mean surface temperature on Earth. You see the spike in 2024, which, as you know, has been concluded to, for the first time, breach 1.5 degrees Celsius limit. So it's a 1-year observation. So it's not a breaching of the Paris Agreement, because it's not a 10-year average breaching, but it's a 1-year experience, which is very significant, by the way, because 2024 is also the year with the most expensive invoices being sent back from the planet in terms of human damage from droughts, floods, heat waves, fires, and human reinforced hurricanes and storms. But I'll leave that aside for this talk. This is what is concerning, that from 1970 to 2014, we have a linear increase, which is entirely in line with the transient climate expected warming. The cumulative carbon equivalent of forcing is linearly related to temperature rise, and we've been following this rate of change of 0.18 degrees Celsius per decade, which is based on this well-established linear relationship between cumulative forcing and temperature rise, which also translates to the climate sensitivity levels, which are normally used as a almost like as the holy grail of climate science, namely the expected global mean surface temperature rise at a doubling of concentration of carbon dioxide, which lands at an average of 3 degrees Celsius at a doubling, which is the number that science has been showing is the most the most likely sensitivity of the Earth system, over at least the last 100 years of science, with an uncomfortably large uncertainty range, though, between 1.5 and 4 degrees Celsius, and I'll come back to that. But that has been basically the guiding principle that has then basically guided all the climate scenarios. It's guided climate policy. It has given us the global carbon budgets. It is what has informed decisions on aiming for net zero emissions by 2050. It is what informs the Fit for 55 policy regime in Europe on cutting cutting European emissions by half by 2030. So this is really important, that the 0.18 per decade has been the scientific basis upon which all efforts on climate mitigation has been guided. And what you see is that from 2014 onwards, we seem to deviate away from this linear trend. And we have an acceleration jumping up to 0.26 degrees Celsius per decade. It's not statistically verified, but it's more than just an outlier point causing a bias. And there's reason to look into this deeper. There is a scientific debate going on this issue right as we speak. Three major candidates to explain this are what you see here on the screen. Is it that we are paradoxically actually getting rid of air pollution, particularly in cities and overseas from commercial shipping? And we know that air pollution, aerosol loading of sulfates and nitrates, which I know you're doing brilliant research in Bangalore and at your institute led by Bala and colleagues, understanding that aerosol loading is actually a cooling agent overall, a net cooling agent, a significant net cooling agent. And thanks to the fact that we are today making some very significant progress in reducing aerosol loading, meaning cleaning up the air in cities across the world, that paradoxically, that positive impact of reducing health impacts of air pollution, paradoxically, may be leading to a bump up of the rate of warming. The second candidate is albedo changes, that more water vapor in the air, but also interactions with aerosols, but also tree lines moving increasingly northwards, and also rapid ice melt, overall makes the planet darker, absorbing more heat. Could that be a reason for explaining this increased rate in warming? And the third one is the overall risk of losing carbon uptake capacity in the biosphere, in intact nature on land, basically forest systems, and in the ocean. And we see many scientific papers now exploring this issue. One paper came out recently confirming that the ocean is having the same trend line. This is atmospheric temperature rise. Here you have the summary showing that the ocean is also jumping from a 0.17 degrees Celsius per decade rate to a 0.27 degrees Celsius rate. So the entire planet seems to be shifting over the last decade from one linear trend to another linear trend. And this is particularly worrying because what you see here is sea surface temperatures observed across all the months of the year. The gray lines here are the observations from 2006 until 2022. And then you see the one gray line which suddenly jumps off the chart, which is 2023. And then in orange, you see 2024. And in dark red, you see 2025, meaning basically the observations up until we meet today. Now, this is really a concern because this sudden jump, which is for one calendar year, both in the atmosphere and in the ocean, in the order of 0.3 degrees Celsius, is not only completely off the charts. I mean, remember that what we see from 1990 up until 2022 is a deep concern. That's what we call the climate crisis. That is that we are anthropogenically causing rapid global warming, but it's been linear. It's following this 0.18 degrees Celsius per decade rate, which is the big concern. And then suddenly, on top of that, you get this abrupt, unexplained, impossible to reproduce in models so far, jump up to this new level, which you see here in orange and red. And what makes, the whole debate even more severe is that, of course, we recognize that one explanation to this is that it's an El Nino year, 2024. And we know that El Nino years gives this spike in warming. And we know that this is a super El Nino, and a super El Nino is a human reinforced El Nino. But that cannot explain such an extraordinarily big jump, because in those gray lines, you also have the last El Nino, 2016. You also have 1998, which was a super El Nino. And not only that, we are now back to a La Nina function of the Pacific Ocean. And normally January 2025 should therefore, of course, be cooler than January 2024. Well, that is unfortunately not the case. As you see, the dark red line here shows that we continue following a high rate of warming. Now, I believe that a significant part of the answer is on this graph here. This is the Forster et al. Graph on overall effective radiative forcing in terms of watts per square meter of human heat injection into the planet. And what you see is above the zero line here, there's a whole messy set of lines, but look at the violet or the magenta line, that is carbon dioxide. And the dark fat line here is all the gases. That's the cumulative. It includes all the non-CO2 gases. It includes aerosol cooling and carbon dioxide. And up until you see a point up until roughly 2010, 2015, carbon dioxide follows the big fat line. So basically, warming non-CO2 gases, which is black carbon, nitrates, methane, cancel out the aerosol cooling, which you see below the zero line here. And look at that line under the zero line, how air pollutants cool the planet around year 2000, equivalent to more than 1 watts per square meter. I mean, a major reduction in warming, equivalent to, according to the IPCC, something like 0.5 degree Celsius. But look at what happens. Suddenly, you get a turnaround around 2010, and that cooling contribution is reduced. So from 2014, you see above the zero line that the black fat line suddenly deviates away from carbon dioxide, meaning that the overall radiative forcing simply is no longer aligned with carbon dioxide. The warming gases simply outcompete anything on the cooling gases. This is definitely one of the factors, but still the jury is out, because what you see here is a summary from a paper by Gößling et al. That came out very recently, that draws the conclusion that of the 0.3 degrees Celsius jump that we saw in 2024, only 0.1, a third, can be explained through natural factors like a volcanic eruption that occurred in 2022, the solar cycle reaching a maximum, and the sulfate regulations of reduced sulfate emissions, aerosol emissions from commercial shipping. So 0.2 or 2/3 remains to be explained. And the big question is this related to new feedbacks in the Earth system, which would suggest that the planet may be losing resilience? And the papers on this are out, for example, on a darkening planet. We have the great work by Jim Hansen and colleagues on aerosol loading. And we have the Global Carbon Project's updates on the fact that 2023 and 2024 did show a significant sign of reduction of land carbon uptake, not a collapse, and certainly something that was expected given that it's an El Nino year, which El Nino years normally lead to less carbon uptake because photosynthesis is impacted by droughts and floods and you get more fires. But what you see here on this graph is really important because above the zero line, so what you see on the x-axis, by the way, is from 1850 until today. It's a whole global carbon cycle. Above the zero line, you have fossil fuel emissions in gray, land use change in orange. Is it all of this that is causing the temperature rise on planet Earth? As we all know, the answer is no, because in dark green, you have the uptake of carbon in the ocean. In light green, you have the uptake of carbon on land. And that's the one I was highlighting, that we see a sign of reduced carbon uptake on land, even though it's difficult to say whether that's a trend. But in the end, it's only the blue part that remains in the atmosphere, causing the global energy imbalance that leads to the 1.54 degrees Celsius of warming in 2024 and the 1.3 degrees Celsius of 10-year average warming. And the big worry, of course, is the moment the planet loses this capacity to provide the green wedges here, then of course we are in deep trouble, because that would lead to a planet that has a feedback where it can no longer buffer the anthropogenic pressures. And you know the buffering here is enormous. Actually, every year, on average, for the past 100 years, 50% of our climate debt, of our burning of fossil fuels and cutting down of forests, does not remain in the atmosphere, causing the climate crisis we're in today. It's been absorbed by intact nature on land, the roughly 50% of remaining natural ecosystems on land, and the ocean. So this is the largest subsidy to the world economy, and we're totally dependent on it to be able to have a stable climate future. And there's been papers coming out showing signs of losing carbon sink capacity on land. So in summary, we are seeing a trend line of the first indications potentially of a planet losing resilience. We're seeing a tendency of accelerated warming, and that there are probably multiple factors explaining this, but they're all together showing signs of a weaker planet. Climate, cloud dynamics, changing albedo, changes in carbon uptake capacity, and shifts in aerosol dynamics, which is not only a question of anthropogenic emissions, but also interactions with cloud dynamics. So that is one set of evidence that supports my starting point, so to say, why we need to be now recognizing the need to be governing or be stewards of the entire planet, because we're putting the entire planet on the line. Let me then shift now to explaining scientifically why this is so incredibly decisive for our future on Earth. And this comes from paleoclimatic data, which in my view is very humbling. It's humbling well beyond science. It's actually quite an emotional insight. And the story goes as follows. What you see here is planet Earth's journey for the past 400,000 years. You see its global mean surface temperature on the y-axis. The zero line here is the pre-industrial 14 degrees Celsius line that we've had during the Holocene. If you start in the plate to the furthest right, you see 1.2 degrees Celsius. We actually at 1.3 on a mean temperature rise. We're actually following a pathway that takes us to 3.1 degrees Celsius by the end of this century. A temperature which I would call to be nothing but a path to disaster. It's a temperature we haven't seen on planet Earth for the past 4 million years. But if you then go to the left, you see this narrow corridor. That's what I call today the corridor of life. This is the range of variability in life support on Earth, manifested as temperature, since we left the last ice age. So you see, we leave the last ice age some 18,000 years ago. We're in that deep blue part in the middle plate. We leave the last ice age, and then we enter this extraordinarily stable, narrow life corridor, which is 14 degrees Celsius plus minus 0.5. You see it here, 0.5 degrees Celsius of variability. We were hunters and gatherers back in the Ice Age here. We've existed on planet Earth for just two ice cycles, which you see further to the left here. We've been modern humans on Earth for the past 250,000 years. We leave the last ice age as hunters and gatherers, a few million people on planet Earth, and we enter this narrow cylinder. And the first thing we do is we go through the most important revolution of the entire civilizational journey for humanity on Earth, namely the Neolithic Revolution. We shift from being hunters and gatherers to domesticating animals and plants to start cultivating our food, and we settle down as sedentary communities, which enables us to start differentiating technology, innovation, and develop the civilizations as we know it. And we have more and more evidence that the reason why we do this is that the planet settles down within this very narrow range of climate stability, which gives us hydrological stability, which also gives us a settling down of all the biomes on planet Earth. So agroecologically, all the savannas, the grasslands, the peatlands, the wetlands, the rainforest, the temperate forest, the boreal forest, the coral reef systems, the whole overturning of circulation in the ocean, the hydrological cycle, spring, summer, autumn, winter, rainy seasons, temperatures allowing for planting and giving us 120 days of cultivation. All of that settles down once Earth is within this narrow cylinder. Outside of that cylinder, it doesn't work. There is no stability. You cannot trust the hydrological cycle. You cannot trust the temperatures. You cannot rely on the ice sheets. You cannot rely even on sea level rise, sea level stability. So essentially, everything settles down and it becomes worth investing in life support, which takes us from a few million people to 8 billion people on our way to be more than 9 billion people. So it's not surprising that we scientifically today can say with very high degree of certainty that the Holocene is the only state of the planet we know for certain can support our world. We've lived outside of the Holocene. We have lived as modern humans outside of this cylinder, of this life support corridor. I mean, we've lived through 2 ice ages and 1 interglacial, but we have no evidence whatsoever that can support the world as we know it. And if you drag the life corridor even further back, actually 3 million years back through the entire Quaternary, we've never, according to the latest science, exceeded 2 degrees Celsius of warming, and deep ice age is -5. So this wider corridor here is, in my view, let's say, the absolute largest expanse within which modern humans can survive on planet Earth. So we're following a pathway that will push us outside even of a wider corridor. So that is really dangerous. And we know that this is all about the energy imbalance on planet Earth. We know that 90% of the energy imbalance caused by fossil fuel burning is not in the atmosphere, it's in the ocean. So there you have a proof of the biophysical, an additional proof of the biophysical resilience of the planet. So 50% of carbon dioxide is absorbed in the ocean and on land. And 90% of the heat is absorbed in the ocean. And then another 4% of the heat caused by our fossil fuel burning is actually consumed to melt ice. And 5% is actually absorbed on land. So it's only 2% of the heat that we have caused through fossil fuel burning, the imbalance that we have, the stress on the system that we've caused, that is causing the climate crisis as we discuss it today in terms of temperature rise with all the extreme events we're seeing. So of course there's reason for being concerned when the planet shows its first signs of shifting away from that stability. And here you have, among many scientific efforts, but this is unpublished work so far, where we're trying to explore what's the future of the Anthropocene? Where is the Anthropocene taking us? And what we conclude is that the window is still open to follow the green line here, where we are, deviating away from unmanageable outcomes, which requires decarbonizing the world economy within the next 20 years and coming back within planetary boundaries to secure the resilience of the biosphere. But the path we're following is actually that middle of the road path you see there. And this is run with an Earth system model called ClimareX. It's a middle of the road EMIC. It has basically very, very fundamental, basic functioning that aligns with all the big Earth system models that are established in the IPCC. And still, it shows what you see here, namely that if we allow ourselves to reach 3 degrees Celsius by the end of this century, even if we stop emitting greenhouse gases at that point, we won't come back. That we get stuck up at this high level for the next 1,000, actually in this case, 2,000 years. And if we have underestimated climate sensitivity, if what I just have summarized so far in terms of these signs of feedbacks and sensitivity in the system would apply, meaning that the climate sensitivity may be slightly higher than 3 degrees Celsius for doubling carbon dioxide, then we would follow that upper path, which could lock us into a hothouse Earth new equilibrium state of the Earth system. So we're talking about big challenges. That's why we published quite recently a review paper. I'm just highlighting that because it might interest you, showing that we are way outside the green space, the safe operating space on Earth, and that the only choice we have today is transformation. There's no linear solution to a safe landing anymore. We have to veer off danger. Danger is coming further and further into the burning embers, high risk red zone here, and turn back very, very rapidly. And I'll come back to what that implies. But all of this is also evidence-based, based on the risk landscape we're facing. And I just want to point out that planetary boundaries are informed to define the safe operating space from what you see here, namely the mapping of tipping elements of the climate system. These are the 16 tipping point systems that scientifically are proven to regulate the stability of the climate system. Many of them are down in Antarctica. You have them in the oceans. You have them in the big biomes. You have them in the Arctic. These have been listed in the IPCC, but also now, for the first time, given a burning embers assessment of the likelihood of crossing tipping points. So what you see here are these 16 biophysical systems that contribute to regulate the climate system. In the burning embers with here is the range of uncertainty in science. The further you go to the right, the higher the likelihood of crossing the tipping point. On the x-axis here is the temperature, the global mean surface temperature. The circles here is the median assessment of the likely temperature at which they are likely to cross their thresholds, which means a shift from generically a self-cooling capability to self-amplifying, basically accelerating the rate away from stable climate conditions. And I want to get two messages across here, basically. It's just that look at the top 5, which are put there under the current danger zone. These are the 5 tipping elements that are likely to cross their thresholds already at 1.5 degrees Celsius. This is what makes 1.5 in the Paris Agreement not a target, not a goal. It's a limit, a biophysical limit. You don't want to risk the Greenland ice sheet, the West Antarctic ice sheet, all the tropical coral reef systems, abrupt thawing of permafrost, and collapse of the Labrador Sea current. Of course, there's uncertainty ranges here, but the average likelihood we assess in this David Armstrong McKay et al. Paper is at 1.5 degrees Celsius. So this is one assessment, and you may ask yourself, is this something that comes just from one research group? Well, this is one research group in collaboration with many international scientists, with Earth Commission, Exeter University, Potsdam Institute. But look at the IPCC. Here you have 5 IPCC assessments from the third assessment 2001 until 2022. Again, IPCC burning embers, darker red, higher likelihood of causing large-scale singular events, meaning basically causing irreversible changes. In 2001, as you see, the likelihood of that occurring was put at red at roughly 6 degrees Celsius of warming, which basically means that the scientific conclusion was zero risk. Nobody was suggesting that we would end up at 6 degrees Celsius of warming. But look, as science advances, the likelihood of causing irreversible changes goes down, down, down. And the more we understand of the Earth system, we're now actually concluding that the risk is in between 1.5 and 2 degrees Celsius, which is very much in line with what I just shared with you. I just want to tell you also that there's frontier science showing that these tipping element systems are interconnected in cascades, particularly the connection between the Greenland ice sheet, the AMOC, the overturning of heat in the North Atlantic, how it impacts the monsoon systems that can accelerate dieback of the Amazon rainforest, which also can accelerate the melting of the West Antarctic ice sheet because warm surface water would gets to a large extent stuck in the Southern Ocean if this overturning is shut down. I also want to share with you that 2 of these tipping element systems, the AMOC, the Atlantic Meridional Overturning Circulation, the North Atlantic Overturning Circulation System, and the Amazon rainforest, which, as you saw in the previous graph, has this very wide uncertainty range, and the average temperatures are somewhere between 3.5 and 4 degrees Celsius before potentially crossing a tipping point. But there's more and more science showing that we may be wrong there, that the AMOC may actually be closer to a shutdown than we have previously thought, and that we know with a high degree of certainty that the AMOC has multiple stable states, and that there is several occurrences over the last 100,000 years when the AMOC has shut down, and that we understand the physics of this, that it is a thermohaline pump that gets shut down because of dilution of the salinity pump from melting fresh water from ice sheets. And that we also have new papers coming out showing that if it would shut down, it would lead to a catastrophic event that would hit the entire planet, because you would get a regional cooling. That's what you see in this blue blob up here, because when the warm surface water flows from the Southern Ocean up to the Gulf Stream area, when it reaches the southern tip of Greenland, it releases that heat to the atmosphere, increasing the temperatures in this part of the northern hemisphere. And then it sinks thanks to being saline, warm water, which is heavy, high density, and it sinks and flows back on the ocean floor back to the Southern Ocean. But if the Greenland ice sheet melts very fast and dilutes this saline water, the density goes down and it sinks slower. But the key is that a collapse of the AMOC would lead, as you see, according to the latest analysis, to significant acceleration of warming in the rest of the planet. And it would lead to, very likely, a collapse of the monsoon over the Amazon rainforest, which means that you would actually have a global impact of an AMOC collapse. And then the second case is the Amazon rainforest, where the climate assessment is that the threshold may be somewhere between 3 and 5 degrees Celsius. But when you bring in ecology, and particularly deforestation, the range of temperature at which the large parts of the Amazon rainforest could tip and irreversibly move towards a degraded savanna state may go down to 1.5 to 2 degrees Celsius if more than 20 to 25% of the forest cover is lost. And today we are at 1.3 degrees Celsius of warming and roughly 17% of deforestation. So this is a concern which we've been summarizing also in something called the 10 New Insights in Climate Science. And I'm advertising that here, so to say, because we summarize the 10 most important advancements in climate science each year for the climate negotiations. and the Amazon tipping point risks were part of the most recent 10-year insights. So we need planetary stewardship, and planetary stewardship can be guided by the planetary boundary science, which defines the biophysical processes that regulates the functioning and stability of the Earth system. We quantify the safe operating space, what you see here in green, with the tipping point science, but also with reference to the Holocene variability of change. We don't want to move too far out of the variability of change during the past 10,000 years. We've identified the 9 processes that together regulates the functioning of the Earth system, climate just being one of 9, but you have biosphere boundaries, a biosphere integrity, land system change, the hydrological cycle, the nitrogen phosphorus cycle, but of course also the ocean stability, aerosol loading, the stratospheric ozone layer, and novel entities, the risk of us loading the Earth system with so many artificial chemical products like PFAS and nuclear waste and microplastics that it could irreversibly impact on the genetic composition of species. The latest assessment is what you see here. 6 of 9 boundaries are outside of the safe operating space, and as you see, many of them are in the high risk zone. Yellow is the zone of uncertainty, what we call the danger zone. We also know that these boundaries interact very closely, so you cannot, to put it simple, you can actually not deliver on the Paris Climate Agreement only by phasing out coal, oil, and gas. The transgression, the breaching of the biosphere boundaries, the boundaries you see to the left here on biodiversity, land, water, nitrogen, and phosphorus, can on their own make us fail on delivering on Paris, even if you phase out fossil fuels. So you need a planetary approach to be able to have a safe landing, even if you focus only on climate. We can then scale these down to biome level. Here you see an effort of showing the transgression of the land system boundary in terms of biomes on planet Earth. As you see, the dark red are biomes that are already way into the transgression zone. Yellow is the Amazon rainforest, which is in the danger zone. And this is a way of guiding also investments into stewardship, or let's say implementing policies on land management. We have been able to do this updates once every 7th year so far. We have now decided that that is no longer good enough. And from September 2024 at the New York Climate Week, we announced publicly that we're going to do an annual update on the planetary boundary science. We have called this a planetary health check. And the health check was described, as you see here, using an equivalent of a blood sample test. And in green, you see the safe space for the 9 boundaries. And then again, the burning embers assessment of risk. And we confirm that 6 of the 9 boundaries are outside of their safe space. And the arrows show also the direction of travel, which unfortunately show that we've not turned the corner yet. We're still moving along a dangerous road. We've now committed to do this every year. So to put it simple, we're going to take the planet to the doctor for a full health check each year. And we think that is necessary. When you have a chronic disease, you don't want to come to the doctor every 7th year. You want to come to the doctor frequently, and you want, of course, to get a cure. We assess, when you put all the boundaries together, that the planet is outside of the safe space. But as you see here from our assessment, which is admittedly based very much on expert elicitation and a statistical summary of the bound transgressions, that we are not yet in the dark red for the planet as a whole, which actually gives us 2 key messages. One is that we are in deep danger. We are in the danger zone on planet Earth. So it's not so surprising. Actually, the planetary boundary science confirms a planet losing resilience, confirms a planet that is showing the first signs of accelerated warming, because we are allowing ourselves to undermine the strength of biodiversity, oceans, land, fresh water. But it also tells message 2 that it's not too late, that the planet still shows this remarkable biogeophysical resilience to be able to buffer, it still is dominated by negative feedbacks. The planet is still absorbing more heat than it is self-amplifying. And this is, of course, our hope, so to say, and what we need to act on. In the final few minutes, just to say that this all translates, every boundary translates to a budget translates to a pathway. So for climate, it translates to the global carbon budget. The global carbon budget is rapidly disappearing. We're down to 200 gigatons of carbon dioxide remaining. This gives us very nervous numbers because 200 gigatons is only for a 50% chance of holding 1.5. If you want to have a slightly higher chance of success, we're down to 150 gigatons, which is equivalent to like 4 years of emissions. But if you do not bring in carbon dioxide removal technologies, we actually have to go even faster, because the only reason why we can have an orderly phase out of fossil fuels is that the climate modeling scenarios have built-in assumptions on negative emissions at very high levels, and I'll show you that in a final slide here. Another key conclusion, unfortunately, is that we have loaded so much heat into the system that even though I would argue that 1.5 degrees Celsius is still possible to hold, it's no longer possible to hold without overshoot. And that's what you see here. These are the IPCC scenarios in the C2 RCP 1.9 family that still holds 1.5, but after significant periods of overshoot. So I think we have to be ready for that, a period of, to put it simple, it will get worse before it potentially gets better. But all of this requires that we actually phase out fossil fuels. We also know that planetary boundaries can be used in economics much more actively. In Davos World Economic Forum, we produced a report showing that a planetary boundary approach is needed to guide the stability of economic development, that we're ready by 2035 are at risk of losing 7% of annual earnings if we do not move ourselves back into planetary boundaries. The latest climate economic analysis, you may have seen this, shows that we are already today committed to very large income losses, potentially up to 18% of GDP by 2050, which of course is really worrying. And this is from that paper. And what I find particularly worrying is that the dark red regions are those that are projected to be the biggest losers in terms of loss of income, while the blue regions are paradoxically potentially going to have a maintained or even rising GDP. So this is a deeply, deeply unfair outcome, and we know this so well, but it also is confirmed again. We also know that the world has not turned around to move back into planetary boundaries. This is the great work by colleagues at Leeds University, showing on the x-axis the number of planetary boundaries that are transgressed. So further to the right, the worse you are in really implementing or moving into the safe operating space. But on the y-axis, you have the further up you are on the y-axis, the larger number of social parameters that we really aspire for, like human development index and life expectancy and gender balance and education, the better we score. So you want to be as high up on the y-axis as possible, but you want to be furthest to the left on the x-axis. So you want to be where that green circle is, which represents the donut economics of Kate Raworth. And it's very clear. Here you have all the countries in the world, and nobody is in this upper left-hand corner that we all aspire to. The rich countries in the world are in the upper right-hand corner, performing well on the social indicators, but doing it at the expense of the planet. And developing countries are not impacting on the planet to a significant extent, but are also failing or not scoring as high on social well-being. So here you have in a nutshell the challenge we're facing. We have a journey ahead of us. This is also unpublished data. We need to, in record space, phase out fossil fuels in gray, transition the agriculture from the dark brown wedge to the orange wedge, from source to sink, scaling negative emissions in yellow, and maintain the biosphere capacity to take up carbon. So all of this shows that even if we only focus on the Paris Climate Agreement, we need planetary boundaries to succeed. we need to manage all what I call today the global commons, meaning not only the systems outside national jurisdictions, but all the big biophysical systems that are proven to regulate the stability of the planet. So we published very recently a paper in PNAS redefining the global commons to say that tipping point systems should actually be considered legally as planetary commons, as global commons. And you see the list here, and we won't go through it, but I just remind ourselves that any biophysical system on Earth, be it the Greenland ice sheet, the monsoon system, the AMOC, or the Amazon rainforest, that we all depend on. Every individual on planet Earth depends on the stability of these systems for their own human well-being, irrespective of where they are located. This is a new situation. And we brought this into the Earth Commission, which is an international global science mechanism to assess the safe and just boundaries. So we brought in the social sciences. Time is up here, but just to say that the safe boundaries is what you see here in the red and green, confirming the planetary boundaries essentially. But when you bring in justice in terms of significant harm levels to people, not surprisingly, the just boundaries for climate, in this case, for air pollutants and for nitrogen, become more stringent. The safe space is reduced if you really take people harm into consideration. And the harm for climate is, of course, based on extreme events, based on lethal heat, based on the hundreds of millions of people who are affected already at 1 degree Celsius. So the safe boundary may be at 1.5, but the just boundary is considered to be at 1 degree Celsius. So I close with this slide. Just I think all of this leads to the conclusion, not only that we need to be stewards of the planet, we need to redefine sustainable development, that it is no longer about reducing environmental impacts, it's about prosperity and equity within planetary boundaries. And that this is a pivotal point, that we now have a choice. Either we continue sliding down into a dead end of a business as usual that will just erode life support and reduce our opportunities for human well-being and equity, or we transform and aim for a safe landing within the safe operating space of a stable, resilient, and life-supporting Earth system. We've come to that point. We have no choice, but that is what we have to endeavor for. Thank you very much, and looking forward to some questions and discussion here. Thanks.
Thank you, Professor Rockstrom. We do have a lot of questions in the chat. Would you want me to call it out, or can you see it from the chat?
Why don't you call it out? I think that's easier for me, actually.
Yes.
Thanks.
First question, it's from BITS Pilani, Goa. There is a class of around 40 students who are attending. And the question is, with 6 out of 9 planetary boundaries outside the safe operating space, what is your assessment for Earth's health today? And what is the outlook for humanity? Do we still have fair probability to bounce back?
Yeah, no, it's an important question, and I kind of covered that a bit quickly, perhaps. So on the first part, 6 of 9 boundaries are transgressed, and that leads to the conclusion that Earth's health is in a bad shape. We unfortunately need to be honest and clear there that we have a real challenge on our watch on planet Earth, and it's important to recognize that it's not only the climate system, it's also the hydrological cycle with all the extreme events in terms of water scarcity and floods and droughts. It is biodiversity in particular that we are risking the stability of large ecosystems. It is land system change, it is nitrogen phosphorus, it's the ocean stability. And all of this together, pollutants and chemicals as well, leads to the conclusion that Earth health is under jeopardy. Now, but what I also try to convey, which I would say, of course, science has a normal distribution itself, and you have you have those scientists who are kind of playing down risk, and you have those scientists who say that we have already gone too far, and that there is no window of a, let's call it a manageable or positive future. I think in that whole diversity of scientific evidence, that's what I tried to show, that we assess that the average point is that yes, we are in danger, but no, we haven't lost it. It's still, the window is still open for a transition, what you would call then bouncing back. And the reason why we conclude this is that we have no evidence so far that any one of the big tipping element systems have already shifted from what we call negative feedbacks. It's not very pedagogic to call them negative, but we love negative feedbacks. Negative feedbacks means dampening feedbacks, feedbacks that reduce stress. And essentially all the tipping element systems, or not essentially, all the tipping element systems in the Holocene state are dominated by negative feedbacks. They absorb carbon, they reduce extreme events, biodiversity buffers, oceans take up heat. All of this is negative feedbacks. So far, even though we have signs of these systems coming very close to the edge, we don't have evidence or conclusive information as if they have tipped over. But the acceleration of warming is the first signs of worry. So we may be at an early stage of seeing the first signs of weakening, but only that. So I would say that the window is still open for turning back. That's what natural science says. That's what Earth system science says. The problem, of course, is that when that is connected or collides with political science and social science and economics and let's call it the real world out there, then you become less optimistic, because unfortunately there are no signs today that we are capable of collective action at the planetary scale, that we are able to trust each other, work together, align with science, and deviate from the risks we're facing. So, but I want to differentiate these two, because you cannot on natural scientific grounds say that we cannot solve this. I would say that natural science, climate science says we can solve this. The question is rather, are we willing to solve it? Are we willing to take the decisions? It's our choice. And the choice is a social choice. It's not a physical choice, if you see what I mean.
Yeah, the next question, we've got two questions from the Divechar Center auditorium. If you could come to the, yes, mic and speak.
Hello, can you hear me?
Yes, I can hear you.
Yeah, Dr. Rockstrom, America, the largest cumulative CO2 emitter, has pulled out of the Paris Agreement. What is your judgment about the impact for the next 10 years?
Yes, thanks. No, that's a really important question. And it is, of course, a very negative development, and it's unacceptable, and it's irresponsible. And in the end, it's also self-destructive, because it will hit back on the US society, US citizens, and US economy. But that said, your question is, will it, in what way will it impact on the world? And I would say that the jury is still out, because it depends on how the world outside of the US reacts to this now. And if countries like India, China, Indonesia, but also, of course, the European Union and Brazil hosting the next COP30 decides to stay on course, to step up ambition, and to not allow the US, I would call it even undemocratic behavior and irresponsible behavior to impact on the efforts to continue delivering on the Paris Agreement, then I think this can, just like Trump won, could potentially basically solidify actually the commitment to climate policy. What worries me most is the other trajectory, which unfortunately we see signs of, which is that the new administration's misconduct in the US, that legitimizes misconduct in other countries as well, or at best that it leads to slowdown of efforts in other countries. And this would be, of course, then we really are sliding along a very dangerous path. So it is very much, to be seen here. But if you get more nationalist, populist, short-termist, egoistic behavior in other countries as well, then of course you could get a self-propelling trend in the wrong direction. Then finally, just to say also that, of course, what worries me as a scientist is the misconduct that the US administration is now, imposing on science, threatening science and pulling out of the IPCC. So not only from the UNFCCC and the Paris Agreement, but also from the IPCC. And as you may know, the US is actually the technical support unit from Working Group 3, the scenario working group of the IPCC, and they have slashed the funding and they have forbid any American scientists to go to China, where the IPCC now has its planning session right as we speak. This is, I would argue, completely unacceptable and can have long-term impacts, because the US has been a very important provider of open global public common goods on, the NOAA monitoring, the NASA monitoring of ocean temperatures, of ocean acidification, the carbon dioxide curves. All this data is fundamental, and the US has been, and hopefully will continue to be, an important provider of this, decisive data. But it's so I'm worried also on scientific grounds.
Thank you.
I see one more hand raised from the Divicha auditorium. Is there anybody else who has questions for Professor Rockstrom?
No questions, madam.
Right. So we have a question from Emma Martin, more about localizing effects. She says she's developing an operational framework to drive a system approach in her workplace. And she's joined the network to try and understand how we make any meaningful progress given the state of the overarching operating system. So, do you have any words of advice on how to conceptualize local to global on the sustainability path? And is it multi-level transformation?
Yeah, that's a big question. What I would advise her is, we are working very hard on translating the planetary boundary science into operational tools across scales for different sectors. I mean, everything from businesses to countries to communities. And the Earth Commission is leading this work on translation, but we're also working increasingly with the World Economic Forum, but also the World Business Council for Sustainable Development, but also with cities like Amsterdam, on how to implement a more holistic approach to sustainability, a quantitative but more holistic approach that kind of aligns with the safe operating space of planetary boundaries. And that could be, I think, my advice, to follow up on that and see if there's anything that can be applied in her context.
Thank you. We also have I'm allowing the mic here for Sailesh Rao. He has a question more on fossil burning and also the animal agriculture. Sailesh, you can put your question across. Your mic is open.
Thank you so much.
When we burn fossil fuels, we're also emitting cooling aerosols. Whereas when we do animal agriculture, there is no co-emitted cooling aerosols. And because of that, Wedderburn Bishop has found that animal agriculture has caused 52% of the warming to date, while fossil fuels have caused only 18% of the warming to date between 1750 and 2020. Yet no one seems to be focusing on animal agriculture. So any comments on that?
Yeah, no, I mean, you're absolutely right. There's a need to include the whole animal agricultural area, and I think there needs more attention there. I fully agree. At the same time, I would say that there is at least an increasing recognition, and I could, for example, point you to the Eat Lancet Commission work, which is also showing, which I'm sure you're aware of, that animal-based agriculture is not only a significant part of emissions and warming, but also that it leads to unhealthy diets, and that healthy diets are more aligned actually with Indian traditional diets, and that is not necessarily a vegetarian diet, but it's at least a significant reduction of animal-based protein, and that this in turn can have a win-win effect both on human health and on climate. So yes, and there's much more needed to reduce emissions from agriculture at large, given that it's the sector that has the single largest emissions of greenhouse gases, very much due to the nitrous oxides and the methane. So there's more focus required there.
All right, thank you. Next question is from Hari Shankar from Bangalore. He says that the analysis shows that there are 6 tipping points that have crossed the limits. His question is there any strategy that your team is working on for each aspect to reshape each tipping point over time, and how long does it take to go back to its original state?
Yeah, so, well, to begin with, our science shows that 6 of the 9 boundaries are transgressed, not that that 6 of the tipping points have been crossed. So the tipping points are, let's say, a subset of the planetary boundaries, and the planetary boundaries are quantified in a way to try and protect the tipping element systems from crossing their tipping points. And we know, which I tried to communicate, that what determines whether the Amazon rainforest or the temperate forest or the coral reef systems are on the right, on the safe side or the unsafe side of a tipping point is not only climate. It's also land system change, eutrophication, aerosol loading, changes in the hydrological cycle. It's the planetary boundaries interact to determine the stability of these systems. But we're not suggesting that 6 tipping point systems have crossed their thresholds. We're just saying that we use the risks, the positions at which tipping points are at risk of crossing their thresholds as a scientific guide to where we quantify the safe boundaries. And but your question is still valid. We have 6 boundaries outside of the safe space. So how to come back? And there, you know, it sounds a bit perhaps it comes across almost a bit arrogant, but the answer is actually quite simple. We know as a I would even argue as a well-established fact that the most rapid way to come back within the safe operating space for essentially all the boundaries is an energy transition away from fossil fuels and a food system transition away from unsustainable conventional agriculture. These 2 alone, just these 2 alone, would take us a very long way back within the safe space. It won't be enough. I mean, the built environment, resource extraction. So moving towards circular resource use and the whole waste management in our rapidly urbanizing world are fundamental components as well, of course. But when you look at the larger picture, if you want to stop loss of biodiversity, stop loss of biome, I mean, what is it that is the predominant cause of us expanding land area into intact nature? It's agriculture. And when you look at the biggest consumer of fresh water, it's agriculture. When you look at the largest cause for nitrogen and phosphorus overloading of nutrients in aquatic ecosystems, is agriculture. So however you twist and turn this, I think we definitely know how to turn this around. And not only do we know how to turn it around, by the way, we know that the scalable solutions are not fantasy. It's not utopia. I mean, we can actually transition to sustainable, resilient farming systems, and we can actually deliver renewable green energy systems even without subsidies today, and still outcompete coal generated electricity on any market in the world today. So we have scalable solutions. We can do it within our current economy. And not only that, we know that essentially on all these transitions, we get win-win outcomes, better health, more resilient societies, more fair distribution of wealth. It's quite interesting that it's absolutely doable. The challenge is that it is a fundamental transition away from our current societal structure. So you have many vested interests that kind of hold on to status quo. And secondly, admittedly, the transition is a big transition. So we're talking investments at large scale, which is a big challenge, particularly in the global south, because of credit worthiness and interest rates and access to capital. And it's also something that cannot be done linearly. We're beyond linear change. We are now at a non-linear change, meaning exponentials, and that is, of course, very difficult to move so fast as is needed. But I would say that the light in the tunnel, in my view, is that on every boundary that is transgressed, we have scalable solutions. I come back to that. It's a choice whether we fail or succeed. It's not kind of predetermined. It's not like a natural law that we won't succeed. It's really our choice.
Next question is from Gemma. It seemed like same on what Emma asked about the operational issue. So she has a question saying, how can you advise on how one can move from global scenarios like SSPs and RPCs to a national and regional application so that they can operationalize this necessary stewardship in a local way?
Yeah, no, you're putting your finger on a major challenge, and I would say there's a lot of research moving in this direction to connect the scales and also in integrated assessment modeling work and to have much better resolution. And I think we are doing some good progress also on I mean, look at the Global Forest Watch or all the satellite-based effort of mapping all the sources of methane emissions and nitrogen oxide emissions and the biggest carbon dioxide emitters. So I think we're better at connecting the scales from the planetary level to the local level, but you're right, there's more work needed here, and remembering again that the only way to succeed, I would argue, is that we have universal rules, so that you cannot have today one nation or one economy or one society that goes all alone much faster towards applying, let's say, sustainable quantifications across all planetary boundaries without having similar kind of policies for the market at large, because we live in such a globalized global economy that it's difficult for for societies to, I should put it this way, the only reason why consumer goods are artificially cheap is that they're subsidized by the planet. Well, as long as economies are allowed to trade artificially subsidized goods and services from the planet, then of course it's difficult for societies to suddenly factor in the true cost and go fully sustainable. So you have to be, we have to have regulations like at the World Trade Organization or at the UN level that creates leveling playing field for all economies. And this is of course difficult in the world of today, where we're rather moving away from these global agreements. But that's something that again needs to be worked at, and I think countries like India, being such large economies and such large societies and such important players on the global scene, can and should play an important role here, just like the European Union and China and other big nations or big economies. But this is part of the challenge. And talking about challenges, Smriti, I should say that my time unfortunately is up. I need to rush into the next
Yes,
next meeting here.
I know. We did shoot another 15 minutes. The questions were there and you were there to answer. But I think with that, Professor Satish, is there something you would want to add before we end it?
Once again, thank you very much, Professor Johan. So we will see you sometime in future in person. We very much would like to welcome you in person to our center at some point. Thank you for delivering this lecture.
Thank you
No,
very
and-
much. Yes, thank you to both of you and also to all the audience. And also today marks the National Science Day for India. So it's good to have this lecture along with the Jeremiah Grantham. And thank you everybody for attending. Thank you so much. Goodbye.
Bye. Thank you.
Thanks a lot. Thanks.